All right, so we are back with the next session here at the Blockchain Community Day 2024. And this time we are going ahead with our next speaker, Andrei Silviu Dragnea, who will be conducting a workshop named Using Rust Custom Allocations to Optimize Solana Compute Units. Hi, Andrei, how are you?
Hello, I'm very excited to be here. And
Yeah.
the talk today will be quite low level, but I'll go step by step, and I'm curious about the questions at the end.
Yeah, thank you so much. We'll be having 1 hour long workshop. That's why I think it's pretty enough to have everything in detail so that everybody could understand the whole thing, considering that Rust is not an easy thing, I would say, compared to other uh, languages. And I think we can now see your presentation, and I would like to ask to our audience to leave your questions in the live chat, in the comments. If you have any questions, address them directly to Andrei, and I will help you to read those questions aloud and sort them out. I think that's it for now. We can see everything on the screen. Good luck to you, Andrei. The mic is yours.
Okay, thank you. So, hello everyone again. Let's get to work. I will start this presentation by having a short introduction on Solana terms so everyone knows what we are talking about. As you might know already, Solana transactions can contain one or more instructions. Each instruction in a Solana transaction can call only one Solana program and has two inputs, a list of accounts and an instruction input array of bytes. An instruction can also call instructions of other programs as part of its execution through a mechanism called CPI, which comes from cross-program invocation. Solana accounts also have a data field inside them containing an uninterpreted byte array. Solana programs are just Solana account where the data field contains Solana bytecode for that specific smart contract. And native Solana programs are programs deployed at predefined addresses on the blockchain and are implemented as part of the Solana runtime itself, for example, like the system program. Let's dive a bit deeper into what the Solana program runtime is and how it runs programs. So as I said, Solana programs are compiled to ELF shared objects containing SBF bytecode. SBF bytecode is a variation of the Berkeley packet filter format bytecode that is borrowed from the Linux kernel virtual machine that is used for filtering network packages. And also, the SBF bytecode is interpreted by the Solana virtual machine. So basically, when a Solana program runs on the blockchain, it runs in a constricted environment of a VM, where we are going to focus next on the memory layout of a Solana program at runtime. So the address space of a Solana program is fixed and is laid out as follows. As you can see, we have 4 addresses important in the memory space of the program. The program code starts at 0x1 address. I will just read the addresses without zeros because there are a lot of zeros and there are hex values. Stack data starts at 0x2, heap data starts at 0x3, and program input parameters start at 0x4. So basically, a Solana program has a heap and a stack as a normal program at runtime. It has some program codes just as a normal process at runtime, and also has some program input parameters at this address. We'll focus next on the program input parameters because we want to see how they are laid out in memory and if we find some invariance there. If we look here, I highlighted some Rust code that shows the binary layout of program input parameters. So as I said, a Solana program invocation has a list of accounts as input. The number of accounts given as input is U64, that is at the beginning of this address 0x4 that I mentioned before. Then we have a duplication marker because basically some input accounts can be duplicated. So two input accounts in the input array can refer to the same account on chain. And in this case, the runtime will just mark this as duplicated. Each input account has a few flags. One is if the input account is a signer or not, if it's writable, and if it's executable. Also, there is data len counter, which shows you the original data length of this account, because as I said, each account has a data array inside it. The key is the pub key of the account. The owner is the owner of the account, because in Solana, each account has an owner as the account model. Next is the LAN ports associated with that account, number of LAN ports that account has, and the data len, the final data len is the actual data length of the account and represents how big the data array for that account is. There are also some constant assertions, which are basically some assertions that are verified at compile time. So this whole calculation here is 96 bytes long, and it's very interesting to see that the first account data address is fixed for any Solana transaction that you will ever encounter, and is basically equal to this value, 0x4 and the 6 at the end. What this means, it means that for any Solana transaction, a programming invocation that you have, when you call it, the Solana runtime will fix the first account at a fixed address in the address space of the program. And this is a very important invariant for us when we're going to look next. As you can see here, we have an example of a Solana program entry point. This is the beginning, the main function, let's say, of any Solana smart contract. And if you add this assertion to any Solana program, it will be true. So as I said, if you have at least one account, the data field of that account will have a start address of 0x4 and a 6 at the end. As I said, this assertion is always true, and it's true only for the first account input of a Solana program invocation, because the rest of the account offsets depend on the length of the data field of the first account. So if the first account is smaller or bigger, the next account offsets will depend on this data field length. So they are not fixed. How you can validate this? Of course, you can validate it with any on-chain program where you have this assertion, but you can validate also locally using Solana program test framework. But it's important to set it up using an SBF shared object and not a natively built Solana program, because you can use Solana program test in two ways. And you cannot use a natively built program because the memory map of that natively built program does not respect the Solana SBF ABI. Basically, the memory mapping is different, because when you natively build that program, you basically run it as part of a test in the address space of a normal process on your local machine, which could be a Mac or a Linux or Windows machine. So this will not work. But it's interesting to see that this assertion added to any Solana program will still be true. So what we have so far, we have a memory region at a fixed address that we saw before, which is mapped to the data field of a first Solana account and instruction. What can we do with it? Basically, if we have the same first Solana account as input for two instructions in two different transactions, this allows us to persist a memory region of the Solana runtime across transaction boundaries, which sounds interesting and scary at the same time. And my next question would be, why not putting our program heap there? From a normal operating system point of view, this is similar to putting your heap of your usual process in a memory segment that is mapped to a file, memory mapped to a file, and to reuse that heap across multiple invocations of the same program. While it's technically possible, it's not very simple to implement on a traditional operating system, modern operating system, because of the address space layout randomization mechanism, which is a security mechanism on modern operating systems that shifts randomly the start addresses of the memory segments of a program on each programming invocation to avoid attacks that can exploit constant memory layouts. For example, if your stack or your heap would always start at a fixed address, some hacker might exploit this in order to gain control of your system. Okay. As I said, let's focus. So far, we focused on the program input address and how the program input accounts are laid out in memory. Let's talk about the Solana program heap. By default, Solana programs have access to a 32 kilobyte memory region that can be used as a heap at the address 0x3. To facilitate fast allocations, the default allocator defined by the Solana runtime is a bump allocator. It is defined using the global allocator mechanism of the Rust runtime. And this heap does not support free or real lock, so it leaks memory, but it's fast because it only basically allocates memory immediately without managing freeze or real locks, and it is okay for most Solana programs. However, Solana program heap can be increased on a transaction basis if needed, up to 256 kilobytes by using the special request heap frame instructions extraction of the compute budget Solana program. So basically, if you need a bigger frame, a heap frame, you can request it by the runtime from the runtime, and it will give it to you. Solana programs that need a custom heap that might need to use more memory than this and need to free unused memory, they can define their own allocator using the same global allocator attribute and the custom heap feature of the Solana program framework. Okay, let's talk about a bit how you define a custom allocator in Rust in general, not related to Solana. So if you need a custom allocator in Rust, you define a struct that will implement the new allocator. You implement an unsafe trait, which is called global alloc from the Rust standard library. You install the custom allocator using the global allocator attribute, as in this example. As I said, this is the struct that you define. This is the implementation of the global alloc trait, which has two important functions, methods inside it, alloc and dealloc. And then you install the custom allocator, defining a static global variable with this attribute on it, and the runtime will know how to pick it up and use at runtime. And a good custom allocator to use in Solana programs that we at Neon EVM use is the linked list allocator crate. It's a low-level crate that can use a linked list based heap that is initialized in data region of your memory map that you give it when you compile the program. So, some conclusions about the Solana program heap. It can be increased from 32 kilobytes to 256 kilobytes. But in our Neon EVM case, the need for a persistent heap is not necessarily related to its size, but to the fact that Solana defines a thing called compute budget, which is a list of limits that a transaction has to respect during its execution. And one of those limits is related to compute units. What are compute units? Basically, are some basic operations of the Solana virtual machine that runs Solana programs that limit the number of computations that you can do during one Solana transaction. The Solana runtime has a maximum limit of 1,400,000 compute units per transaction. The default limit is lower, it's only 200,000 compute units. And this limit can also be increased by the set compute unit limit instruction if you need it. But it's still sometimes not enough for us. And we'll talk next why this is the case. So as some more context about what Neon EVM is. So Neon EVM is an implementation of the Ethereum virtual machine as a Solana program, and it uses Solana account as EVM storage. So basically, we run a VM inside another VM. The Ethereum virtual machine as a Solana program inside the Solana virtual machine. Ethereum transactions compared to Solana transactions can be very big both in size and the amount of computation they do. And the problem is that Neon EVM sometimes cannot process Ethereum transactions inside only one Solana transaction because of this compute unit limit. So the EVM state needs to be persisted across multiple Solana transactions. And why do we need that? Because we need to pick up from where the previous transaction finished and reinitialize the EVM state and then start from that point onward until we finish the Ethereum transaction that is executed by our EVM. So the EVM state currently is serialized at the end of a Solana transaction and deserialized at the beginning of the next one until the whole big Ethereum transaction is processed. And this repeated serialization and deserialization of EVM state consumes compute units by itself. So basically, in our Solana program, we waste a significant part of our compute units just trying to reinitialize the state of the EVM from a previous iteration instead of actually running EVM code, EVM bytecode. So how can we avoid this repeated serialization and deserialization? Well, by allocating the EVM state inside a persistent heap across transactions. And let's see what we can do about it. So the Solana account can be used, the first Solana account of a transaction can be used as a big heap for one Solana transactions or more Solana transactions. And how can you do that on implementation level? First of all, can you do it? And the answer is yes, and it's very simple. Basically, you just have to define a custom allocator using the global allocator mechanism. You just change the default start value of the heap from the traditional heap of a Solana program to the address, the fixed address of the first Solana account in a transaction. And you have to be careful to provide to that program a first account whose data field is big enough to contain the whole heap of your program that you will need. And it's interesting that the newly allowed maximum heap size is 10 megabytes, which is also the maximum size of the data array for a Solana account. So basically, with this hack, you can increase the size of your heap if you need it up to 10 megabytes from the 256 kilobyte heap size of a default Solana heap. But also you can use the Solana account heap as a persistent heap across transactions, as we said. And it's interesting how you do that, because Rust makes it hard to do, because Rust is a safe language. So basically, let's say that you have some state that you want to persist between two Solana transactions. And that state, let's say that is behind a box pointer, because we need it to have it on the heap. In our case, it's the EVM state, but let's, for the sake of the example, think about an array of bytes that will be our state. The problem is that this value will need to be accessible in the second transaction and following transactions too. So we need to allocate it on the heap with box new, and then use box into row to leak the pointer intentionally. And this is another interesting thing. How do you know on the next Solana transaction where the initial box allocation was done on the heap? Basically, you had a pointer on the heap that you lost because the first transaction was finished, and you need to find it again on the next transaction. The solution is to store it at the predefined fixed address in the Solana account data array in order to know where to find it at the start of the next Solana transaction. So for the sake of example, I chose the location for this pointer to be right at the beginning of the first Solana account data array start address, so at 0x46. And the actual heap will be shifted a bit with 8 bytes to the right to the address 0x468. So basically, it's the size of the value of the initial address plus the size of usize, which is the size of the pointer type on Solana virtual machine, which is 8 bytes. And we do this because in Solana programs, you cannot have static mutable variables, static global variables. Basically, in a normal Solana program, in a normal Rust program run on your local machine, normal programs have at runtime a memory region where global variables are stored. But this is not present in a Solana program, because Solana programs can only access a runtime heap and a runtime stack, and all the inputs data they can access is from Solana account. This is the runtime model of Solana, so we cannot have global variables in a Solana program. But we can define our own global variables inside the Solana account at a fixed address. And we do just this. And this is an example of doing this. So as I said, there are some const assertions that are validated at compile time. This is the state pointer address that is equal to the first account data address, and it has the address 0x46. Here we check that the alignment of this address is okay in order to access the data without runtime error. Then the state pointer, as I said, is defined from the state pointer address. The heap start address, as I said, is shifted a bit. It's basically the first account data address plus the size of usize, as I said on the previous slide. This is the assertion for the value of the heap start address. The heap length, the maximum heap length in this example that we can have is basically 10 megabytes minus the size of the state pointer that we use. And this is also where we define the heap pointer. And this over here is basically the method which is used to access the heap in our global alloc trait implementation. As you can see, this heap here is the one from the linked list allocator crate, and we initialized it only once on this if path. And if it's already initialized, we just use an unsafe block to access it through this heap pointer that is fixed to this address over here. Okay, now let's think about what we need in our Solana program in order to access the global state, because so far we only talked about the heap itself, how it's defined, how we use the global allocated trait to install it and everything. So the Solana program needs instruction logic to initialize the linked pointer, to use it across multiple transactions, and to deallocate the linked pointer when not needed anymore. And it's a very interesting thing. If everything works correctly, apart from all the pointers reachable from the linked pointer, so basically if you have a tree of allocations and all the state that is reachable from your state, like other heap allocations allocated inside your state object, they should be deallocated at the end of each Solana transaction by the Rust runtime, because an ideal Rust program at the end drops every value and deallocates all the memory of the heap that was allocated during its execution. These are the primitives that I used in my example program in order to initialize the state data, to access it when needed, and to drop it. So let's look over it a bit. The init state function is basically a function that takes as parameter the initial value of this state, which is a vector of bytes. As I said, it will be our example. It's a function that is used to initialize the cross-transaction state. It moves the input value to the heap over here by using box new, and then links the pointer to avoid dropping it at the end of the transaction. At the end of the first Solana transaction. So basically, at the end of the first Solana transaction, the only thing on the heap, on the persistent heap, will be this pointer allocation. Then we use the state and state mode accessors in order to retrieve a shared reference, which is mutable or not, depending on what we want to access. And the drop state basically is a function that will be called in the last Solana transaction processing in our EVM example, for example. And drop state, what it does, it reinitializes the box from the linked pointer, and it drops the pointer in order to deallocate that memory from the heap. Now, these functions are very important to be used correctly because they are dangerous. What happens if you use the state or state mode function before using init state? Basically, you would access undefined data from the heap. So this is not okay. You have to be careful in your logic that you first init state in the first transaction, use state and state mute in all other transactions where you need it, and drop the state only at the end. And after dropping state, you don't call these two functions afterwards. So let's think about a bit what could be the problems of this hack, let's say. If the Solana account data size is less than the Solana program expected heap size, the program will panic with an access violation. So basically, if your Solana program account input is not big enough to fit all the heap that you want to allocate during that runtime running of the program, of course, the runtime will fail with an access violation. But this is easy to fix. You just have to be careful to allocate Solana account which is big enough. What happens if you use the same heap through a lot of Solana transactions? Heap fragmentation can show up, and this could be avoided by using two heaps. The normal heap of the Solana program for things that are only needed in your current transaction, and a global heap that where you only allocate the state that is reused across transactions using the allocator API to crate, which is basically a crate which duplicates all the unsafe APIs that are present in the current standard library, Rust standard library, and are not stabilized. And you can, for example, have a duplication of the VEC implementation from the standard library. So when you use that VEC from allocator API2, you basically allocate that VEC on your custom heap, and these two heaps are managed separately in two different memory regions in order to avoid fragmentation. The third big problem is undefined behavior, because basically you hook up a heap for your program at runtime from a previous transaction, and you have to be sure, but by your security model of signers and transaction processing, that you don't end up with a heap that is not yours or it's not known to you before, because this could end in security breaches. And also the very interesting thing is that the allocation itself consumes compute units. Because if you think about it, when the free method of an allocator is called, of course, it has to do some logic in order to track what regions of memory will be freed and everything. So sometimes maybe just using a bump allocator with a big heap, big enough heap size, could use less compute units than a heap which doesn't leak memory. But this requires benchmarking on a smart contracts basis, so each Solana program could behave differently. Okay. So as a conclusion, Solana runtime memory model is deterministic. This is a very interesting property, and it actually is a property common to many runtimes. For example, even the Java virtual machine and also the Ethereum virtual machine. Basically, all virtual machines, this is why they are virtual, because they have some fixed things inside them, and one of them is the memory model, and where the addresses of different structures are defined, and can be used in novel ways, as I tried to show you in this presentation. And the second conclusion is that the first Solana account inside the Solana instruction can be used as a heap, which can also be persisted across transactions if needed. And the account heap, using this hack, can grow up to 10 megabytes from the maximum normal heap size of 256 kilobytes. This would be my presentation so far. I can also show you the code, and also I want to point out that all the code of this presentation is publicly available on my GitHub, where I have a fork of the Solana program library repo, and inside that repo there is the Rust Summit branch, where everything about this is available for you to play with it, including the Solana program tests that I discussed about. Is the link over here. And we are also hiring if someone wants to join us on hacking Solana and Ethereum. And again, thank you for your attention, and I'm waiting for your questions eagerly. So let's see.
Yes, just give me a second to check the live chat if there will be some questions. 1 second. Yeah, it seems like we don't have any questions so far. So I'd like to ask our audience that we have enough time to ask any questions to Andrei. Just write them down.
I can also share my screen and show a bit of the code that I discussed about. I mean, it's not all the code. I didn't add all the code of the repo in the presentation because it was a bit too much. If anyone is curious about it.
I think that might be useful, since we are going to publish the video as a recording on our YouTube channel, and there might be some viewers who will be watching it not live.
Okay, let's share my screen. I hope everything will look correctly. So entire screen, okay. Can you? Ooh, yeah, it works. Okay.
Oh, okay, yeah, we see it.
Okay, so as I discussed, all the const assertions that can be validated at compile time are here. This is the layout of the input program input parameters that I discussed about. This is the first account data address. This is computed here and validated with this assertion. Here is the state pointer address and the state pointer initialization, the heap start address, the heap length, the heap pointer, also the heap access method that I discussed about. Here is the custom allocator that you can see. It has this configuration for the target OS Solana, because basically when you run tests for a Solana program, basically this code is compiled into contexts. It's all once compiled as a SBF program that we run inside the Solana virtual machine when this is enabled. And it's also compiled as part of the test framework itself. And in that case, you shouldn't have this allocator set up, because basically you would use your Solana allocator in your test program run, and this would mess up your test run. So this is why you have we have this configuration target OS Solana here. This is the implementation of the global alloc trait for our Solana allocator. Here we are using the heap method that heap function defined here in order to allocate and deallocate. These two are just some optimizations of the default implementations in the trait from Rust, but they are not very important for this presentation. And this global allocator attributes on the Solana allocator static variable, as we discussed already. Here are the accessors for the state that I mentioned already. The init state, the state retrievers, and the drop state. This is the process instruction, the entry point of our example. This is the assertion that is available for any Solana program that you will find. And here is a very basic example with a lot of log messages. So basically, this is a very rudimentary program where the y equals 0 is basically the start instruction of the first Solana transaction. So basically here we initialize the state to be empty. Then this is an intermediate instruction that retrieves the state. Sorry, this is the end instruction that queries the state and it drops it. And this is the intermediate instruction here that queries the state, adds an input value from instruction data into this state, and then displays it again. And this is the test, important test that I mentioned about. Basically, here we are creating a few transactions for this program, and we are doing different things inside them. I'm gonna run the example program. I mean, I actually ran it here already. It's basically run with cargo test SBF. And when we run it, okay, I don't know why it failed. Okay, because I forgot to uncomment that line with the global allocator, as I said. Basically, the global allocator was also used as part of our test process. Okay. If we look at the logs of the program, we will see here. So this is the initial persistent heap. It's full of zeros. Then, okay, sorry, there are actually two tests here. This is the first, the test that we discussed about. So the persistent heap is initially empty. Then we add a value to it, this value. And then at the end, we also deallocate it, and everything should just work as I presented, as I showed in the presentation. Okay. Yeah, and that would be it. It's basically a derivation of the cross-program invocation example from the Solana program library, as I said. And this is available on my GitHub, as I said in our presentation too. Okay. I don't know how to stop sharing. Okay. Yeah. So this would be it.
Okay. Yeah, I think there are still no questions for now, but I'm sure there will be some questions after we publish this video as recording. And I believe there will be some people who will be trying to do everything you have just explained. And I will let you know about that if we will receive extra questions about your workshop. I think that's then that's it for now. Andrei, thank you so much for delivering this workshop. I hope that will be pretty useful for our audience, especially for those who are starting their career as blockchain engineers. We'll try to promote your video on the specific audience and target it among our learners of our mentorship programs and different other programs. Thank you so much once again. Thanks to everyone who could participate here during our live session. I hope to see you again, Andrei, on our stage. And that's it for now.
Okay, thank you.
Thanks. Yeah.
Bye.